this is a kind of. Can you hear me now? Actually.
Yeah, I can hear you. The connection quality is not good, but I can hear you.
Oh wow! So it looks like. How about now? Yeah, I'm at home. The internet, quality
Yeah,
is not that stable nowadays. Is
yeah.
this okay now?
Yeah, I think it's okay now. What
It's
about
okay
other
now. Okay.
audience? I think it's okay now. It's very good from my end.
Okay, cool. Yeah, thank you again, for the really nice introduction and for organizing this and other seminars. I subscribe to the channel, and definitely I enjoy many of the talks that I usually cannot make to. So today I'm going to talk about first principles for modeling and controlling human-driven and autonomous vehicles. And this, some of you might be familiar with my research, and I used to focus a lot on methodology. But today, actually, I try to shift my focus a little bit away from methodology, from models. Definitely, we'll talk about them, talk about results too. But we'll try to focus on the first principles and what we can learn from some of this relatively simple first principles, which are kind of like common senses actually. So let's see if it works. Yeah. So this is outline for today's talk.
Well, I think you actually need to share your screen.
Yeah.
Oh, I did not share my screen.
You need to click the yeah. You just try that
Maybe
again.
take the PowerPoint.
Oh, so start to share screen. Oh, okay. Sorry. Is this now? Will this work?
There you go.
Oh,
Yeah.
okay. Yeah, thank you. Yeah, sorry about that. So then actually, I will focus more on the first principles for car following behaviors. Of course, we have lane changing, merging, diverging, and many other behaviors in transportation system. And in particular, I will share with you some results on a collision-free principle and a bounded acceleration principle, and what these kind of principles can teach us in terms of modeling traffic flow and so on. And then share some thoughts. This is not final on how to incorporate bounded deceleration and a bounded jerk. And then finally, I will offer some discussions, some comments on the traffic flow models and so on. So, the transportation sector is undergoing a lot of revolutions, according to UC Davis, where I graduated from. So there are three revolutions: electrification, automation, and shared mobility. And then with these revolutions, we are facing new opportunities and also new challenges in both practice and research. Definitely, many systems will look quite different from the time when some, very classic models were developed. So we need new insights and new ideas. And in particular, for autonomous vehicles, there have been, the trade-off between safety and efficiency, right? You may have heard of that. There's a really high-profile accidents of automated vehicles, but at the same time, Waymo, by Google, their cars tend to be drive, pretty safely, but really slowly. And then how can we, help to address this kind of challenges? That will be very important for the whole society to take full advantage of such new technologies. And I feel that we as transportation researchers can really help, not just computer scientists, not just artificial intelligence researchers. We can play an important role. And this talk will try to deliver that message. So definitely for ideal driving behaviors of autonomous vehicles, there have been some discussions that we want to be, at least several magnitude safer than human-driven vehicles. There have been some data on that. For example, human-driven vehicles, the probability of fatality per hour is 10 to negative 6, and if we want to improve it to 1 over 1 billion, then if we assume driving speed of about 30 miles per hour, then that is about 1 fatality per 30 billion miles. And then, but at the same time, the efficiency. This is very important for the transportation system. And transportation system is supposed to move people and goods, efficiently and of course safely at the same time. So definitely we need to take care of the, efficiency to avoid, a lot of investment, in the space and other, resources. And then, another thing is that ideally we want, these autonomous vehicles to have a human-like driving behavior. For example, car following, lane changing, and so on. Especially in the very, initial stage when we have a mixed traffic flow. And for example, we want to have a similar speed limit and a similar safety cushion, acceleration, deceleration profile. That would be really nice. And autonomous vehicles can be, understood as intelligent robots. And then, the driving task, there are, for as same as the robots, we can be divided into 3 categories: sensing, to understand what is in the environment, especially in the transportation system. The environment is really complex, but it's fortunately we have a lot of sensors, and they are able to sense the environment to pretty good accuracy. And then the second part is to plan the trajectory on the road. And then third one is to really maneuvering the cars. And then by this talk and our study focus on planning. And not only because our expertise, our research interests, actually, the other 2 parts, action and sensing, have been, relatively well studied, or say have been taken care of by other researchers. For example, the action part, it can be built on, control theory, and this has been pretty robust and pretty reliable. And then the sensing part, there have been a lot of sensors, and also the sensing can be verified offline. The technologies can be developed and verified offline. While this planning is a little bit different, this has to be in the real world, cannot be done. Mostly we have to do it in the real world. And there have been kind of 2 approaches. One is based on statistic method, whether it's artificial intelligence or other machine learning, or those statistic methods. If it's based on statistic methods, then that means if we update the code, either AI, those codes, then we really need to test for another 30 billion miles. And then, if you consider that, I don't know if this number was correct, but, Waymo actually tested less than 1 million miles in 2020. So, but on the other hand, if, these planned trajectories are mathematically guaranteed to be safe, to be efficient, and also to have a human-like driving behavior, and then we don't have to go through field tests. But no existing framework, to the best of my knowledge, are amenable to mathematical analysis. So that is where we feel our expertise can be helpful in developing autonomous vehicle, especially in the planning trajectories. And in general, the trajectory planning models can be categorized. First one is, car following model. If we are just talking about car following behavior. And there have been 2 really nice review articles here by Braxton, McDonough, and Seifsterman and Jen. And then these models can be categorized into 3 types. That is my interpretation. One is stimulus response, then the safe stopping distance, and then multi-phase models. Later, I will talk a little bit more about this one. With these models, I mean, most of the models, they have closed form formulations of acceleration rate, and they have nonlinear ordinary differential equations, and they are amenable to mathematical analysis. But it is not sure if these are usually developed to describe traffic flow, but can we use them to guide autonomous vehicles? That is a big question mark. Actually, we did some experiment later. I'm going to show you that. Then the second one is in the field of adaptive cruise control area, or advanced driving assistance system. There have been a lot of studies, and these systems usually comprise of different components like collision and accident avoidance and automatic emergency braking. And there have been a lot of numeric simulations, but there's no closed form formulations. And these are more like different subsystem, and whether they are consistent with each other, and all those questions have not been really answered. And then third approach, of course, is really hot topic is artificial intelligence based model, based on reinforcement learning, but this is a black box, or it's like statistic method. So as we said, such kind of a planning method, planning models really have to be tested in the real world before really implemented. We actually had interest in this using car following models to guide, to control autonomous vehicles. We did, some implementation with such kind of robotic cars. And this, you see this is actually a later version. In the earliest version, actually, we saw the robotic cars collide into each other, literally. I was aware of this thing in numeric simulation, but to see this, happening, even to robotic cars, that was still pretty shocking. And then after that, I realized that, in the car following model, I believe we implemented optimal velocity model. Even the very basic principle, like safety, collision free, was not taken care of. But of course, for simulation purpose, that is fine, right? We've seen, in many simulators, especially during the lane changing, cars can overlap with each other, but who cares? But if we really want to use this at the same time to control autonomous vehicles, that is not enough. So that has been kind of a motivation for me to, look into, the first principles. But, this talk, I want to, try to convey the message that, if we, focus a little bit more on first principles, actually, this can help to develop our own domain knowledge. Traditionally, like car following model, stimulus response, those kind of models, was based on more like of analogy. Okay, but without really getting into the first principles of traffic flow, and those those models are useful, but looks like did not capture the most fundamental properties of traffic flow, and then cannot be used to guide autonomous vehicles. And then next, I want to talk a little bit about what should be good first principles for car following, right? Before that, I want to get some general research methods. One is based on first principle. This is well known and applied a lot in in other area like a Newtonian paradigm. And then the second approach is data-driven or empirical methods, and the third one numerical simulation methods. All of these are important for us to discover knowledge. And but first principles, some simple first principles actually of course need to coupled with mathematical modeling, mathematical analysis, and solution methods, and actually can lead to a lot of profound insights. And said first principle have been widely used in the science and engineering, and actually Einstein even argued that the grand aim of all science is to cover the greatest number of empirical facts by logical deduction from the smallest number of hypotheses or axioms. Here, hypotheses, axioms, they are equivalent to principles. And then this is also practiced by Elon Musk, in SpaceX and many other pioneering engineering projects. So we want to do that, and even in the very recent modeling of COVID, there have been some successful modeler. I believe is one data scientist, a graduate from MIT. He actually single-handedly beat many other institutions in modeling, and one approach is to build his model based on some simple, common senses. Okay, so first principle for traffic flow is not well known, and actually in a Cross in a very famous 1998 dissertation said that no first principles of traffic flow are known, from which models of different resolution could be derived. And then, but actually, D'Agenzo use some first principles to criticize the second order continuum models. Later, I will have some comments on that too. So basically, he argued that the laws assumed to govern the microscopic world accurately should represent the behavior of the real traffic vehicles. So, but what are the behaviors? What are the laws, right? But it turns out, actually, as early as 1945, two physicists already introduced some, principles of physics. I mean, that is a third reference, and apply this to traffic movement. Basically, they introduced so-called influence space. Nowadays, this is equivalent, to safe stopping distance, right? There's a reaction time, there's a deceleration, braking distance, and there's a safety cushion. And this is a very interesting article, but it's not well known. And then actually, he showed that with such kind of principle of safe stopping distance, then we can show that this guarantee no rear end collision, that is collision free, and there's no you also lead to a fundamental diagram. And then traffic flow can be traffic dynamics can be described by a bunch of trajectories on the road, and also by a 3D surface, right, which was first constructed in this article. And then later, actually, Laval and Leclerc show that actually there is a really nice trinity in the traffic flow in terms of flow, schedule, and trajectory, right? And then, of course, correspondingly, among these three variables, if we choose one as a dependent variable, and then the other two would serve as coordinates. And these three variables would represent the flow, trajectory, and schedule, basically, and they have their applications in different areas in traffic flow in transportation. And then talking about that, actually, these days there will be saying that in the physics, in fluid dynamics, then the corresponding coordinate will be called as Eulerian, and then this one will be Lagrangian, and then the third one will also be Lagrangian. But actually, these days I like to call this as flow coordinates, trajectory coordinates, schedule coordinates. I feel that is kind of more intuitive for traffic flow. But anyways, from this we can define well-known first order variables on flow rate, speed, pace, and so on, and also higher order derivative. And then now let's get to the first principle. I mean, first principle actually should be very simple and like common sense already, and like a collision free, like should be forward traveling. Okay, and there's speed limit, and also we tend to maximize the speed, for the efficiency, subject to all kind of constraints. And then there's a fundamental diagram. Okay, and there's a bounded acceleration, bounded deceleration, bounded jerk. And among here, fundamental diagram has been verified through observations. And as said earlier, from Harry study, fundamental diagram actually is a consequence of the safe stopping distance principle, and as well as clear and free. So I would like to start with this, and then using mathematics, I'm not going to formula. Using all these variables, we can define all these principles mathematically. Okay, so these basic principles, this kind of promotion, and it was introduced in chapter 3 of the book that I recently published, which aims to be a textbook. That was really really challenging. But hopefully you guys will like it. But these basic principles are common sense. It said this is consistent with our daily driving experience and consistent with the traffic rules, vehicle characteristics, and the empirical observations. And also, it has been used in the adaptive cruise control system standardization. And so this seems to make sense, and they're very simple. But in the history of science and engineering, some very simple rules, principles actually can lead us really far along the way. So let's take a look at the collision-free principle. What we can learn from this on the modeling traffic flow. And we know that the LWR model basically, in this sense, is the conservation law plus a fundamental diagram, right? And in particular, when we have a triangle fundamental diagram, that leads to new or simplified kinematic wave model and the equivalent, the car-Fowler model. So, one way to solve it is to use a cell transmission model. Cell transmission model is based on a discretized version of the conservation law, and also the very special way to calculate, the boundary flux. And based on the demand and supply concepts that were introduced by D'Agenzo and Lebesgue in 1995, 1996. So, in the such cell transmission model, actually one important decision is to choose the delta T, the time interval, and the delta X, the cell size, right? Traditionally, mathematically, we have a so-called cell. We have the CFL condition. Okay, that is well known in numerical methods for solving differential equations to guarantee the consistency, stability, and so on, the nice properties of numerical methods. But actually, it turns out that this can be interpreted as the collision-free principle. And I'm not going to get into the details, but the basic idea is that if the speed density relation is non-increasing and the flow density relation is concave, both triangular and Green-Shields fundamental diagrams certify this thing, and then the CFL condition is equivalent to the collision-free condition. When I teach traffic flow theory class, I have a lot of difficulty in motivating what is CFL condition, right? I come from like applied math. I learned quite a bit on the numerical solution methods. I understand the stability, consistency, and so on. But what is that about in the traffic flow? Actually, it turns out it's collision-free. Actually, later I will show that collision-free condition is even nicer than the CFL condition. Then the LWR model actually can also be written as a second-order formulation if we use some hyperreal or the non-standard notation of epsilon. And we basically have a relaxation term. For those of you who are familiar with second-order models, basically we have a relaxation term, but this relaxation time is effectively just a time step size, and in the continuum version, it goes to 0. Okay, then this can be written as equivalent car-Fowler model, Okay, if we are using certain discretization method, and then here in this this car following, but this is continuum car following, because here the delta m may not be 1. Okay, delta t may be really small. And then we also have this collision-free condition. And then earlier in Leclerc, Laval, and Chevalier, there's the self-air condition, right? Now let's compare the self-air condition and the collision-free condition. It turns out again for the nice fundamental diagram, they are equivalent. But if we have non-concave fundamental diagram, okay, like this one in Kerner and Kahnhauser, then these two conditions are not the same. Basically, the collision-free condition can give us, actually for one delta t, basically collision-free condition means that the delta t should be small, while in the self-air condition, the delta t can be relatively larger. And actually, on the right-hand side with the simulations for a braking problem, it turns out if we use the self-air condition with such a non-concave fundamental diagram, because this braking problem, eventually the cars will settle down at the jam density and jam spacing. So this non-concavity would actually would matter. So with top, I believe is the collision-free condition. So then everything will be fine, no collision-free. I mean, the cars will be about 7 meters away, something. But on the bottom, if we just use self-air condition, but violate collision-free condition, actually you can see that the spacing will be much smaller. It will be just 1 meter, much smaller than 7 meters that we set. So that just shows that in traffic flow, the collision-free condition is better than self-air condition, actually. And then the collision-free condition actually can also give us some guidelines on how to discretize car following model. For example, when we discretize the car following model, when we convert the continuum model into the trajectory coordinates, we would have such kind of partial derivative. And one natural discretization is this backward discretization. And this is anisotropic. Basically, it means that the acceleration should be impacted by the vehicle in the front, not the the back. Okay, so this is a natural discretization, and also with respect to time, and we want to discretize the acceleration explicitly, but the speed implicitly. Okay, so you can see this is the implicit discretization. This is explicit discretization. So actually, this is called symplectic, Euler method with respect to time. So these are natural, but actually this can be shown. These are necessary to guarantee collision-free. For example, if we try non-anisotropic discretization, then like all other difference methods, they all violate collision-free condition. And then similarly for the time discretization, if we both use explicit, actually this has been widely used in solving many car following models. And then in this case, actually show that it violates the collision-free condition too. So it just shows that this collision-free condition actually is very useful when we get to discretize the continuum model, discretize the car following model, and then of course, I mean, collision-free should be satisfied when we try to control the autonomous vehicles, right? Second principle I want to talk about is bounded acceleration. Okay, due to the vehicle kinematics, I mean, acceleration got to be bounded, but we know that in the first order model, LWR model, in the Newell's model, the acceleration rate can be, very, very large or infinite when vehicles accelerate away from, intersection. And then, the model is, we can use the non-standard second order formulation of the LWR model plus an acceleration bound, because basically this left-hand side, can you guys see my cursor here?
Yes, we can.
Okay, that's nice. Yeah, thank you for the confirmation. So basically, this is acceleration. Okay, before the acceleration is given by this non-standard relaxation term, but now we, it can become very large because this is infinitesimal, very small. Now let's add one bound to it. That will give us naturally bounded acceleration, right? This is equivalent to Lebesgue's two-phase model, and this is a second order model. It's no longer first order model, okay? And then if we have triangle formula diagram, this turns out to be, the bounded acceleration version of Newell's simplified Kaufman model. And this is also equivalent to, the very famous Nager-Schreckenberg cellular autonomy model. Of course, the deterministic version. There is a stochastic version. And with the bounded acceleration, right, this very natural traffic flow should be like that. And then we found that the reaction wave actually would not be the same as the reaction wave in the LWR model. For example, if we have triangle formula diagram, we know that all stopping vehicles, if they originally stop at the intersection, and then when the signal turns from red to green, they would immediately accelerate to to this point, to the critical density point, right? In the LWR model or Newell's simplified Kaufman model would teach us this. But in reality, there's a bounded acceleration, and then there's a transition, continuous transition of density, and also, of course, of speed. If you look at the slope of the tangent lines, then we have speed. Speed slowly increases. And now, I mean, that is on a homogeneous road. And actually, it turns out on an inhomogeneous road, there's a like a bottleneck. There's a length drop bottleneck here, or if we have a sag bottleneck, we have slopes, or when we have tunnel bottlenecks, then we have a bottleneck. And then in this case, inside the bottleneck, the fundamental diagram actually gradually changes, right, from the outside to the inside. Outside is upstream, inside is downstream. And then you can see that, at one stationary density, flow rate, for example, Q star, and then inside the bottleneck, the speed actually increases, okay, along the location. And then, if we impose the bounded acceleration constraint to it, then we can show that this flow rate under certain situation with the limited length of the bottleneck, with other characteristic of fundamental diagram, then we can show that the stationary flow rate cannot reach the downstream capacity, which is C2. This is exactly the phenomenon of capacity drop, meaning that if there's no congestion, the flow rate can reach the downstream capacity. But there's a congestion, then the flow rate actually will be lower than the downstream capacity. And the results and the model has been verified with real-world observations in Japan, in Kobutoki tunnel, and when the congestion starts, the researchers send the vehicles and driving through the tunnel and repeatedly. And definitely you can see, here x equals 0 is the entrance of the tunnel, and x equal L is the narrowest point according to the observation and the theory. And then you can see the speed profile is relatively stationary, okay, and the speed they are increasing, and this is consistent with the simple analysis from the fundamental diagram. They are increasing, and then there's a boundary acceleration. But of course, I believe in this situation, the acceleration bound is as low as 0.4 meter per second squares and something like that. It looks like the acceleration bound could also depend on location and so on. So that's subject to further studies. And then in another study, collaborated Wada from Japan and Irene Martinez, who is going to finish this year, and we check out the continuum car-falling model of sag and tunnel bottleneck, and we were able to show that this capacity drop indeed can be reproduced in such inhomogeneous car-falling model. Newell's simplified car-falling model and the Del Castillo's car-falling model, and so on. And then Irene further actually applied this model of capacity drop to analyze the optimal location problem for variable speed limits. And such a kind of problem was only empirical, numerically simulation-based study once, I believe, and then Irene identified the problem and then formulate the problem using the boundary acceleration principle, using the concept of stationary states, and so on. And she was able to formulate the problem and then solve and find indeed there is an optimal location for variable speed limit. Basically, the idea is that if this variable speed limit zone is too close to the bottleneck, then the capacity drop cannot be eliminated. It has to be sufficiently farther away from it, but it cannot be too far away, right? If it's too far away, then it will create a queue, and you can further block, upstream on-ramps and off-ramps. So that was a really, really nice study with a novel problem and formulation and solution method. Then, we have, it looks like boundary acceleration is pretty easy to incorporate into the model, and it has been known. But how about boundary deceleration and boundary jerk? This is very important for developed models to control autonomous vehicles, right? Because autonomous vehicles, they really need to satisfy, the first principle. Those are really kind of the first order principles. Okay, it has been shown, it has been certified by LWR model and Newell simplified car-falling model. That's really nice. Boundary acceleration has been certified by these models, but the boundary deceleration definitely is very, very important. This determines the braking behavior, the deceleration behavior, right? That is where the accident can occur, rear-end collision can occur. And also, it's important for designing traffic signals. We know that it's based on the theory of dilemma zone, where, the boundary deceleration is very important to determine, the yellow signal interval. And the boundary jerk is also very important for the comfort of passengers and drivers. But to the best of my knowledge, there's no model that can handle all of this. Okay, I tried one naive way. Okay, because before we say boundary acceleration, okay, nice. Let's use a minimum of boundary acceleration. But how about boundary deceleration? So let's use the maximum of this one. This is not so simple. If we look at simple braking problem, we can prove that this violates the collision-free condition. So basically, it shows that there's a conflict between boundary deceleration and collision-free. That is not surprising, right? If we can decelerate as fast as we can, then we can avoid a lot more collisions. But in reality, it's not the case. So how to do that? I've been trying to build on existing approaches like stimulus response models, but unfortunately, many of these models violate first order principles, like a general model family. It is known but not well known because it's still taught as the first car-following model in traffic flow theory in many classes. This violates, the very basic fundamental diagram principle. But we know that fundamental diagram is necessary to guarantee, safe stopping distance, as shown by Harry and Harry as early as 1945. So this does not work. And the intelligent driver model also have some difficulty. That's why this is the original version. Now there's the enhanced version, and there are still discussions on why they violate this collision-free and other conditions, first order condition. And then there's the safe stopping distance model, like this model, including Gibbs and Cross, and they satisfy the first order principles nicely. But whether they satisfy all other principles, especially bounded deceleration, bounded jerk, is not known. And then there's a multi-phase model, VSIM, behind VSIM, and parameters. They tend to be really complicated. The analysis is not that simple. So, but all of these models offer some nice ideas, and I think it looks it would be helpful to build on them. But first is to really to analyze them, compare them, and using these first principles. Okay, what kind of principles they violate, and what kind of principles they satisfy, and if we can use those components. So that is about the car following model, first principles. I said, I'm working on the model, but the results are not final, so I don't feel ready to share them yet, but hopefully I will have them soon. But then, first principles not only for car following, right? This is just a starting point. And then how about lane changing? How about heterogeneous traffic and network traffic? And actually, it turns out there have been studies in the literature. And of course, I'm really biased here. And for example, lane changing, it was shown by us that lane changing actually it leads to increased density and reduced length. So that will create some bottlenecks. This is consistent with the observation, and that was built on one simple observation. Actually, you can consider the first principle is that one car during the lane changing duration occupies two lanes, right? The vehicles behind it on the current lane, on the target lane, they all have to follow them safely. So based on this one, actually I was able to derive a new fundamental diagram and then kinematic wave theory. Interestingly, lane changing was attributed to cause capacity drop in the Lavin and D'Agenzo 2006. But it looks like from our studies, it's not the case. Lane changes did create bottleneck, lead to capacity reduction, but capacity drop actually is caused by the bounded acceleration. It turns out in Lavin D'Agenzo, that it was based on simulation model with a hybrid model. The car following model actually did have bounded acceleration component to it. It looks like there was a lane changing, there were also bounded acceleration, but it looks like the real cause is bounded acceleration, not the lane changing. On the multi-class fundamental diagram, when we have a heterogeneous traffic, and then we need to consider whether there's a first in, first out principle. And another relatively new concept is unifiable. Basically, if we have a heterogeneous vehicles together, whether we still have one single fundamental diagram, speed density relation for the whole traffic. Then, of course, merge, diverge behavior is really important in network. And it turns out, as early as a self-transmission model, by D'Agenzo, and demand supply. There were priority merge, first in first out diverge. Those can all be considered principles. But of course, these are kind of the macroscopic or phenomenological. And then another very important principle was the invariant principle. First introduced by Lebesgue and Yaran in 2005. And later it was proven that this invariant principle is equivalent to that the flux is the Riemann flux, and the network version of cell transmission model is a Gordon speed. And then on the second order continuum model, actually second order continuum models have a really long history. As long as Lighthier-Witten in 1955, they already proposed one second order model with a diffusion term. Then later, Penn-Whitman introduced this relaxation term. But there's a lot of confusion on second order continuum model. And definitely we see the limitation of first order model. And then one way to address them is to introduce second order model. But as pointed out in 1995 by D'Agenzo and other researchers, and this diffusion version leads to runaway travel and leads to negative flows and negative speeds. And basically this violates forward traveling principle, as we discussed earlier. Again, I mean, this principle is very simple, common sense. But another criticism was taken more seriously. That is the anisotropic property. Basically, in D'Agenzo, it was anisotropic was defined as that the characteristic wave speed should not be greater than vehicle speed, and this has motivated a lot of studies try to resurrect second order models by introducing models with characteristic wave speeds not greater than vehicle speeds, including very famous all-rescue-down model. But it turns out this model violates a fundamental diagram principle. Basically, the vehicles can drive at any speed, even at the jam density. That is not correct. That violates the safe stopping distance principle. But of course, there's one exception, that is Greenberg. This violation of fundamental diagram principle and other first order principles also appear in the Ross 1998, and this was commented by Newer, show that then speed converges to free flow speed at any density, including the jam density. This is one of the very rare comment article in the transportation area. But all in all, actually, whether this anisotropic property is totally necessary, there's I have a different opinion. In the earlier discussions, I already talked about that. Any second order model, continuum model, can be nicely converted to continuum Carr-Forley model, and then we can easily discretize them in an anisotropic way. So basically, there's no violation of anisotropic property. Rather, they actually violate other properties, other principles. So I feel, if we want to develop second order continuum models, it might be more fruitful to consider, like forward traveling principle, like other, well-defined principles, rather than, such characteristic wave speed versus vehicle speed. That is very mathematical or, physical, fluid dynamic physics. It's not that relevant to our traffic flow characteristics, traffic vehicle characteristics, just like self-air condition. And then, of course, can we have principles for other traffic behaviors like demand modeling, where we have a performance function? We have, there's a lot of confusion on that too, whether we have user equilibrium, system optimal, all this choice behavior, and then management principles. planning principles. So I feel this approach could also be really fruitful when we talk about other transportation problem, and then of course in general science and engineering, right? And actually, in addition to those things, our recent studies shows that if we look into the transportation system, we can have different understanding of the space-time flow. Like in a network, actually, if we introduce a relative space dimension, basically we put all trips into the same space-time domain, while the space represents the remaining trip distances. And then actually this will lead to simple model for a network. It's called the Besta model, which was originally introduced by Vickrey in 1991, and it was published in 2020. And then such kind of model has a really nice property that we don't have to take care of the network topology, the origin, destination, and all those things. But at the same time, we still have a good idea. Of course, incorporating network level fundamental diagram, we still have a good idea about the network traffic dynamics, especially during the peak period. And then on the other hand, with such a relative space, the absolute location of all travelers, the trips are hidden. And then actually this leads to very nice privacy preserving modeling and data collection in paradigm. And actually we are exploring these opportunities, how to collect such kind of data, privacy preserving data. Hopefully this will encourage people to share their detailed trajectory data more easily. And then of course the flow does not have to be vehicles. It can be anything. It can be trips, can be goods, and so on. So this framework can take care of that. And in addition to that, actually we can also have some imaginary road. And the time does not have to be within daytime, can also be a day-to-day. And this was shown in a recent study on departure time choice, where if we use scheduling cost as a space, and the time, days as time, and actually the problem, the departure time choice problem, can be converted to a traffic flow problem. Is equivalent to the traffic flow problem when there's a vehicle stop one by one to a red light. Okay, so basically traffic flow can appear in such kind of imaginary space and day to day, and then actually in the social there's a lot of mobility. It looks like it is also possible that we can have even social traffic flow if we can define the time and space nicely, and of course flow nicely. So that just shows that if we get into first principles, we can not only develop our own unique domain knowledge, and it is also possible to make broader contribution to other areas. So that is all for today's presentation. Thank you very much for your patience.
Okay, thank you, Dr. Jin. Thank you for the nice presentation. I believe now we are open for questions. Audience, please feel free to raise your hand, unmute yourself, and ask questions, or leave your question in the chat box. Dr. Jin, I have a question here. I noticed you show some initial thoughts on the deceleration bounds or the bound for jerks. I happen to see some open source code of some linear ACC systems which incorporated the deceleration and acceleration bounds both.
Yeah.
So for the deceleration bound, I was kind of puzzled by their design. Because they do clearly have a linear deceleration bound. It's like opposite of the linear acceleration bound.
Yeah.
But of course, when we speak of deceleration bounds, we need to consider safety. So their design is to first calculate the time to collision factor. So if they fear the time to collision is very short, and they use that factor to release the deceleration bound. So I would like to hear your comments on such design. Do you like it or not, or do you think it's a safe or good design?
Yeah, I don't know exactly, the mechanism of implement that, but to incorporate the deceleration bound, this practice has been done as early as 1945 in Harry and Harry's paper. They already have this, and then of course later Gibbs and Cross and many researchers have introduced this. But then, our preliminary analysis shows that with this implementation, actually, on one thing is that the real deceleration rate could be over the bound. So it's not really bounded deceleration. And then another thing is that it looks like they may not be able to guarantee collision-free principle. So, but then of course in the real world there's a lot of kind of tweaks into it. But I would like to to give it kind of thorough analysis, or using the first principles, start with the first order principles, and then try to analyze it. But such analysis actually involves needs development of new methodology. Actually, here, it said I do have some preliminary results, but they are not final, and I don't feel ready to share them. And definitely need some new analytical framework and new things to understand what is really going on within these models.
Yeah, I feel it's the same for the bound for the jerks. So for all those linear type of controllers, we would like to have bound for deceleration and jerks to improve the driving comfort. But for some safety reasons, if you want to prevent collisions, you always need to release that bound.
Exactly.
So I think that's a problem. It's also partially explained why NPCs become more popular. And if you have longer planning horizons, maybe you can predict some collisions, and that gives you more flexibility to plan more comfortable driving trajectory. Yeah.
Exactly. So, to have such kind of safe, to incorporate safety and bounded deceleration, it looks like, the planning horizon has to be longer. Cannot be, local. So some non-local information needs to be taken into consideration.
Yes. Thank you.
Yeah.
I saw Dr. Lavar raised his hand. Dr. Lavar, you have a question here? Dr. Lavar, we can't hear you. Maybe Dandre, you can go first.
Okay, I still have opportunity. Hello, Wenlong. Thank you very much for the presentation. It was excellent. So I'm also very interested in this bounded deceleration issue, and I just to follow up your discussion with Hao, I felt that probably the bounded deceleration for the jerk should prioritize on the safety rather than the comfort for the emergency event. So And for that piece, I mean, you naturally will always have this case that in order to guarantee the safety, right, you need a very large deceleration. And for that purpose, I think the bound is coming from the mechanical capability of the car, not from the comfort.
Yeah. So definitely, I mean, priority. We should, put the priority on safety. But it would be nice if we at the same time can take care of safety and comfort. I mean, generally the level of comfort is determined by the jerk. If the jerk is too large, then we would not feel too comfortable. And then, yeah, as you said, the boundary deceleration is really determined by the mechanics. And so, I mean, there is a kind of a heuristic way to take care of the things, but my interest is to try to come up with a systematic approach such that all of this can be put into the same model, and this can be mathematically proved. They said this would be very important if we want to control autonomous vehicles. This will save us from many field tests. If it's based on heuristics and so on, then we don't have any guarantee. We are not sure if under certain corner situation whether safety or other things will be violated. So that has been kind of my motivation along for this presentation and also the ongoing study.
That I fully agreed. And I imagine that actually for the challenge is not only from the car following, because imagine that for the car following case, but anybody can cut in anytime. Yeah. So that actually makes it more challenging to maintain the collision free.
Exactly. As said here, I mean, all this is on the car following. For lane changing, for merging, diverging, and all those things, it can only be more challenging. But at the same time, I feel that this is just a starting point. But this approach of looking at the first principles, the very basic assumptions, constraints, and so on, it is kind of necessary. But at the same time, it looks like it's possible to do things. And then this is also our expertise, and we should do that. We have this domain knowledge, not computer scientists, not this AI researchers, and so on. So definitely we want to work together, but I feel this is the most promising area that we can make a contribution. We want to make things as a kind of white box, not black box.
I fully agree with you. Thank you very much for your pioneering work in this area.
Thank you very much. Yeah.
Dr. Lavar, are you back?
Can you hear me now?
Yeah.
Yeah.
Okay, good. So yeah, I wanted to know your opinion of this first principle that I came across. That I think it's the one behind the kinematic wave model with triangular diagram, which comes down to advance if you can.
Yeah. Yes.
So if you have a space in front of you, you go, but if there's somebody, you stop, basically.
Yeah.
Right.
I think that can be if that one I call it maximum speed principle.
Mm-hmm.
So under all constraints, we want to go as fast as possible.
Right.
Yeah. So that is indeed the important piece, and also again, it's as said. I mean, these first principles are not kind of that complicated thing. When I talk about this to students, I mean all students who do not have background in traffic flow theory, they think, oh, this is common sense. I mean that makes sense.
Right, but you can actually derive the model just starting from that sentence. That's what's interesting.
Yeah, maximum speed is one of it. Maximum speed principle and subject to collision free, subject to subject to the speed limit, subject to fundamental diagram. Actually, all these I call them first order principles. Actually, lead to the LWR model basically.
Yeah, but I don't think you need the fundamental diagram though. That I think that's covered in the advance if you can rule.
That one. Yeah, there are different ways actually to present the first principle because, for example, I mean the safe stopping distance principle, which I just got into that very recently. But it turns out actually that covers the collision-free and fundamental diagram principle.
Right.
There might be other equivalent way. Yeah, I think that would be interesting. There might be other, kind of equivalent set of, rules other than, this.
I guess my point, the fundamental diagram shouldn't be a principle, should be an output of the principle.
Yeah, these principles can be kind of phenomenological. They do not have to be. I mean, for example, this safe stopping distance seems to be more behavior, and if maybe we can directly derive those things from safe stopping distance. That would be another way to present it, but fundamental diagram has been verified with observations. So, as said, I mean, in my, view, principles can be, behavior principles, can be, empirical, like phenomenological. As long as they are kind of well defined and well accepted, then they will work.
Yeah, very nice.
Mm-hmm. Yeah.
And my other comment was about the jerk, right? So yeah, for AV vehicles, it turns out to be a key variable, right? Because it gives you the comfort.
Yeah.
So what about coming up with car following models starting all the way from the jerk instead of the usual, which is the acceleration, right?
Yeah, there have been attempts on that. Basically, that is third order derivative, and there have been those models. But the point is that to offer them, will this violate other first order, second order principles?
Yeah.
That is very important to know.
And we don't know that yet.
Yeah.
Okay. Very good. Thank you.
Yeah, thank you.
All right. Did you want to?
Yeah. I don't see any more questions from the audience. I think we can call it a day for the event. And thank you, Dr. Jin. Thank you for coming. It's early and giving us such a nice presentation. And for next week, it will be among the Thanksgiving holiday in the US. So we won't have presentation for next Friday. The week after next week, we will have Dr. Eloisa from UIUC to give us the next ACC webinar, and we look forward to seeing you there. Thank you. Thank you, everyone. Hope you have a nice weekend. Bye-bye.
Thank you very much. Yeah,
thank you,
nice to
Wenlong.
see you guys again.
Thank
Talk
you,
to
Wenlong
soon.
and Hao.
Thank you.
Have a good weekend, everybody.
Yeah.
You too. Bye.